talk of the day and the last talk of the conference is by Wolfgang Pitsch from Barcelona. And he'll talk about a chase for invariants in the Johnson filtration for Casson.
Thank you very much. So I have three small announcements. First, this is of invariance of three manifolds, but my title was already very long, so I just had it now, this three manifolds. Second, I think we would all agree that it's been a very nice conference with beautiful talks so far, and that we should thank the speakers, the organizers for gathering us, and the people who ate the chocolate. Point is that this is a conference on surface bundles, and I will absolutely not speak anything about surface bundles, but on the mapping class group. So let's start with the actors of this very small drama. The first one is the theory of Heegard splittings. So you start by a very nice result of Waldhausen. It tells us that there is a unique embedding of a surface of genus G into the sphere up to isotopy that splits S3 into two handle bodies. And this tells you, so that splits, so this is this standard embedding. So if this is a Bretzel, we live in the complementary Bretzel of this one. And I fix a disk in my surface. And because I don't want any problems with low genus, G will always be at least 3 in this talk. And so this tells us that the sphere is a union of two handle bodies with reversed orientation glued along their common surface by a map that is not IG. Okay, so in a slightly more topical setting, we have the surface of genus G. This is the boundary of the handle body that we can see. And we have a map into the outer handle body, and the push out is our sphere S3. And now let's introduce a set of all closed oriented three manifolds up to oriented diffeomorphism. And we have a well-defined map from the mapping class group. So this is phi 0 of the diffeomorphism of the surface that preserve this disk of the boundary of, if you could, the interior of the disk. And you have a map from the mapping class group into V3 by just taking your sphere, cutting it along sigma G, and gluing back, but before you glue back, you twist the gluing by an element of the mapping class group. So C, I get S3V, which is simply the push out of sigma G is the boundary here, and here I just twist before by glue. And this is well defined, and that's why I need up to diffeomorphism. So of course you represent by some class, and then you construct the push out, and this is well defined. It's well defined, and it is stable in the sense that if you take now the limit of these mapping class groups in the usual sense by gluing tori and extending by the identity, then this is a surjective map. So you can get any three manifold in this way, and producing such a splitting is exactly a Heegard splitting. So now about the kernel of this map. Well, associated to this diagram here, you have also a diagram of mapping class groups. So you have the mapping class group MG1, and then this receives all mapping classes that extend over this handle body, and this is the group EG1. Here you have those that extend to the outer handle body, so this would be AG1, and their common intersection here would be ABG1. And by another theorem of Waldhausen, these are exactly the elements that extend simultaneously on both sides. Extend to both sides. Okay. And there is now this result that these two groups control completely injectivity of this map in a very precise sense. There is a theorem by Singer, which is not the Singer theorem from, I think, 50, I wrote 56, but I'm not sure. 66 or 53, and the following map is a bijection. You take the limit of the double cosets mg1 by kg1 and bg1 by S3. And this is a bijection. So it is well defined and it is a bijection. And in this sense, as a first attempt, you can translate any problem on three manifolds on the problem of the combinatorics of the mapping class group, in particular, of course, the Poincaré conjecture. And if you don't know, there is a paper by Stallings, which is called How Not to Prove the Poincaré conjecture, which is exactly starts from this kind of decomposition. But I'll come back on this Poincaré conjecture. The story didn't stop there, I recently learned. So, what can we do with this? Well, let's take this let's not believe Stallings, and let's try to understand invariance of three manifolds through this bijection. So I have this limit on my equivalence relation. I go to this manifold with a bijection. I have some invariant into an abelian group. I will also ask that the invariant on S3 takes value 0, just to normalize. Of course, this receives all the mapping class groups, and I can compose, and I get a series of maps. And these maps, well, they satisfy three silly conditions. First, FG of the identity is 0. Second, if G plus 1 restricted to MG, 1 is FG. And 3, FG is constant on double classes. And fourth, for the moment, silly observation is that FG is never a homomorphism. Just because there are no homomorphisms. So, but this will be important in a moment. Okay, so these are the first actors of this picture. Our second actor is the Johnson filtration. So we have our mapping class group. The mapping class group acts on the fundamental group of our surface. M1 goes down to P. This is injective, and this is very complicated because free group is complicated. So of course the idea is to approximate this action. And for this, we observe that the action preserves the lower centered series. Of pi, so these are premises with pi and gamma L plus 1, the commutators of A and gamma L. And so we have an action on the nilpotent quotients. One out of 5 out of L. This is sometimes known as the Johnson map, and I just take the kernel of this map. And this builds me a filtration by descending filtration of MG1 that is separated. The intersections of all these groups is identical. And I have a bunch of guys that have, for me, have a kind of nicknames here. So of course, MG11 is Torelli group. MG1, MG1, 2 is the Johnson subgroup. KG1, and the next one is LG. And now we can try to play this game, but instead of looking at all the mapping class group, we only look at these subgroups. So we have a diagram. We have the same game. And I have this limit. MG1 is 3. The limit of the Torelli group with the induced equivalence relation is gives me something. And then I have the limit of KG1, the limit of LG1, and the limit of these groups, or with the induced filtration. So this is 1, this is 2, this is 3, and this is level L. And a priori problem is, well, try to describe these subsets.
But will you tell us what, sorry, what is that thing there? Did you tell us what
S3?
That is?
Just now.
Okay.
Just now. So because we have the migratory sequence, and because homologically elements in the Torelli graph do not act, if you build someone by this Higgs splitting construction, starting with an element in the Torelli group, from the homological point of view, is like Lewin by the identity, and therefore you have the integral homology of the sphere. So these are exactly integral homology spheres. Okay? And it is an exercise in the symplectic group to show that if you start with a mapping class that builds an integral homology sphere, then it is equivalent to someone in the Torelli group. And therefore, this is a bijection, and this is a bijection. And for the moment, I just have here inclusions. And this is an inclusion, and this is, of course, a proper inclusion. Okay. So the first problem, and one of the, let's say, my motivating problems here is problem describe this filtration. So let's play the same game now here, but with the Torelli group instead of the full mapping class group. So I will shamelessly take advantage of the blackboard to just erase things. You take the limit of the Torelli groups to build any integral homology sphere. Start with an invariant, which takes the value 0 on the sphere, and you have a bunch of trigger conditions on these functions fg. And now this is a little less silly observation that this is never a homomorphism. That's a small lemma. Here this is 3. If n has no T portion Fg is never a homomorphism. But of course, this time the homomorphism from the Torelli group to n, this is not zero. And there is a unique invariance for which these restrictions are homomorphism, and this is the rolling invariant. The unique invariant such that Fg is a homomorphism. It's rolling invariant with values in Z mod 2.
So n is an abelian group and f is what?
F is an invariant.
Wait, what does that mean?
A function on the set of integral homology classes.
Just a map.
Yes, just a map.
Okay. Well, that's the FGs. F itself is just a map.
So this constant on double classes, constant on equivalence classes. This is just, I start with an invariant. So this tells me a bunch of maps. Because they have to be compatible with this equivalence relation, this means that when I start with invariant and I restrict from one Torelli group to the other one, then the functions have to be coherent. Then because I have an invariant, they have to be constant on the equivalence classes. This is, for the moment, it's completely trivial. It's just saying that these Fg are given by an invariant of homology spheres. Okay, and this last step here, this is due to Dennis Johnson.
You should also attribute Berman and Craig's need.
Excuse me?
You should mention Berman and Craig's name in that too, right?
Yes.
They just proved it's an invariant.
Right. No, they proved it's a homomorphism.
No, I know.
Johnson proved there was all of them. So.
Yes. Do you want to say what the, and that's invariant of four manifolds? Are you going to say
Excuse me?
what exactly? And the Roekel invariant, sorry, of three manifolds, and oh, I see. No, you did. Sorry. I mean, it all is well lined up. I think.
I mean, really, number one is probably, that's due to maybe Morita or Johnson, isn't it?
Which one?
The first part of the lemma?
Oh, I don't know if it's well. Yes, because it's really a lemma. I will tell you just in a moment how you could prove this.
Okay.
Thing. It's really not difficult. It's really due to the fact that we know the abelianization of the Torelli group and the action of the mapping class group. So,
isn't it true this third one? I mean, you can get any integral homology from the Johnson third one.
excuse me? Yes, I will come to this in a moment. We're the next step. Don't go too fast, don't go too fast. I will run out of paper before I run out of time. Okay, so so what do I need to keep? This one. Just the definitions. This is okay. So one of the difficulties in analyzing this filtration of integral homology spheres is that, as I stated these equivalence relations are somehow not internal to these groups in the Johnson filtration. This means you have two elements in your preferred step of the Johnson filtration. You look at them in the mapping class group, see if over there they are equivalent, and then you declare them equivalent here. So the first step to try to analyze this would be to somehow internalize this equivalence relation on each of these groups. And on the Torelli group, this is not too difficult. I wrote, but maybe it was known before, I don't know. two elements P and psi, one, are equivalent if and only if there exists an element mu in ABG1 so that extends on both handle bodies, elements CA and CB, AG1 in, T, AG1 times TG1, meaning I intersect these groups with the Torelli groups, such that, well, phi is mu, so CA, CB, mu minus 1. So to make things very short, the equivalence relation is, well, take the obvious double cosets and then take co-invariance with respect to the action of ABG1.
So is this group ABG1 a subgroup of Torelli?
No. AB is the intersection of the two groups. So ABG1 are mapping classes that extend on both sides. So it acts by conjugation of the Torelli group. Okay, because it's a normal subgroup. So now, just to tell you how do you prove this, the first part of this lemma. Well, you have an invariant. An invariant is constant on the equivalent classes. Therefore, it is invariant under conjugation by the group ABG1. And you show by direct computation that there are no such homomorphisms. And this is all. It's not very deep. But it's not deep, but not as silly as before. Okay. I don't know. So question is the obvious generalization of this 2n1L true for L at least 2. Meaning two elements in this level L step of the Johnson filtration are equivalent if and only if they lie in the same double coset class with respect to the intersection with this level L subgroup plus conjugation. An equivalent statement to prove this, you should show the following. You take an element in the mapping class group on this group AG1 such that when you look at its action on the fundamental group up to length L+1 commutators, it coincides with the action of an element in BG1, and then you should find an element that extends on both sides that has exactly the same action. And then you will prove this. And this I don't know. Okay. So the last object now is Casson. So let's go back in time. We are around maybe 35 ante Perelman. There are very few invariants of three manifolds that are known, and one of the most important is the Rolli invariant. And there is a question: to take the Rolli invariant, you compute it on a homotopy tree sphere. And easy deal. Okay, so long question, obvious question for one, well, obvious question, obvious way to find a counterexample to the Poincaré conjecture. And in 1985, Casson tells, but obviously does not publish, that he has a lift of the Rolli invariant. So the Rolli invariant R is an invariant mod 2. He has a lift into an integrated invariant, which by construction lambda of homotopy 3 sphere is 0. So let me tell you a little bit about some features of this invariant lambda. So I will not construct it, of course, at some points. But I will, in fact, if I have time, I will give you a somewhat completely elementary construction of this invariant. Okay. So what he proves, so these are facts. There is a unique, there is at most one, that is most one invariant on S3, such that one, the invariant is determined by precise surgery properties, and two, lambda of the Poincare sphere is equal to 1. And these surgery instructions tells you that, well, you have S3, you fix a link here, so it has components L1 equal K, you attach some numbers to these components, and now you perform surgery, any integral surgery on each of these components in order, and this will produce you an integral homology sphere. And this is a trace of the fact that the mapping class will be generated by den twists. And what this says is if you choose a component here, you need some condition of the component, then there is a relation, a precise relation between S3 on the link, S3 on the link minus this component, and the Alexander polynomial of LG. Okay. So now, let's say that for any invariant you can see it as a bunch of homomorphisms in the what remains, and we'll also try to explain you how to see these surgery properties on the Torelli. And then there is a second step, is when we have to construct this invariant. And to construct this invariant, you compute in a very clever way the number of representations of the fundamental group of your three integral homology sphere into SU2 minus 1. And if you have an integral homology sphere, a homotopy 3 sphere, so the fundamental group is trivial, you have only one representation, and the value of the invariant is 0. Okay, but this is complicated. Okay, then some years later, Morita enters into this game. He proves the following. There exist two functions, D and F, on the mapping class group V, which he constructs, such that 1, D plus F is the Casson invariant. 2, F restricted to LG1.
How does it make sense to call it the Casson invariant on MG1, since that's the whole, these are the ones give you homology spheres?
What do you mean?
So this is MG1, right? So this is the whole mapping class group. And so it doesn't...
It's the Casson invariant when restricted
Okay, oh, I see, okay.
to the Torelli group,
Okay.
but they are defined on the mapping class group level, and then he
Right,
restricts.
yeah. Okay.
To get this unicity, he has to go up to the mapping class group. This FG1 is 0 on this step of the filtration, and 3, D is of homological nature. So I will not give his construction of D because it's too complicated, but I have a very elementary construction of D on this Johnson subgroup, KG1. So let's look at the construction. And then you will see what I mean by these surgery properties here. Okay, so we know Casson. There is a paper by Guillou Amarin in French on the Casson invariant, which is called Notes sur l'invariant de Casson, where they explicitly tell this story about the fact that the Casson invariant, there is really two parts, the unicity given by these surgery properties and then the construction. And for lots of applications of the Casson invariant, you do not really need the construction, just these surgery properties. Okay, so how to construct D? A variant of D. Well, let's do like this. We have our Torelli group and its abelianization, which is the image of this Johnson map, is the third exterior power of N1. And 1. Okay, then on this group you have a contraction map into N1 by taking this third exterior power and then intersecting two of the elements and times the third, and then you antisymmetrize this construction. And on N1, you have a bilinear form, which is the symplectic intersection form. Okay. So a bilinear form on the abelian group, this is a 2 cocycle. So you pull back 2 times this 2 cocycle. So you pull back I1, C, pull back of 2 times omega. And it turns out that this is trivial, a trivial 2 cocycle. Because it is a trivial 2 cocycle, it is a co-boundary of a function. So this is, if you evaluate this on 2 guys, phi C, this is delta phi C minus delta phi minus delta C for some delta. Into G. If this delta were one of these functions coming from an invariant, then this would also read as your invariant on this sphere. And then we'll raise up the blackboard in a second. Okay, if this were an invariant, you're exactly telling, well, if you construct this modulary sphere by mass 5C, and you know the invariant on the sphere constructed by phi and the sphere constructed by psi, you immediately get this invariant up to a correcting term, and this is a kind of surgery instruction attached to your invariant. Okay, so now, in this point of view, this surgery instruction is a trivialized 2 cocycle on the Torelli group. And the fact is that you choose any of these trivializations for any delta, you restrict delta to KG1, and this is exactly, if I remember, well, 24 times, where there are 12 factors that come from these signature properties. There is a 3 times Meyer 2 cocycle, and well, in the surgery formula there are these 3 times the first Montagan class, 4 because divisibility by 4 of the signature, and the extra factor 2 is this one. And you choose any one of these, and then you have this Casson invariant, and Morita calls this map D the core of the Casson invariant, because when you go down this Johnson filtration, then it is exactly the Casson invariant. And in fact, well, he published this paper called Cohomological Construction of the Casson invariant 1. And at the end of the paper, he promised that he would show directly that this is an invariant without comparing it to the Casson invariant, but number 2 never appeared. Okay. And so one of my goals was to try to construct the Casson invariant like in a modelical way, following exactly this idea. But before I do this, let me tell you what continued in the story. So then Morita tried to see in this filtration, maybe LG1 builds all integral homology spheres, and therefore you just constructed the Casson invariant completely from cohomological data. And in our first paper, he showed exactly that here you have an equality. Okay? In a few years later, through awful computations, so Gregor reminded me that I gave a series of lectures on how to compute this guy inside here. And after 3 hours of talks, I did not finish the proof. It's not conceptually difficult, but just the computations are absolutely awful. And this is an equality. So then there is a second proof by Gwenaël Massuyo and Jean-Baptiste Mélan using Clasper calculus. And then I recently learned that some Japanese students went all through my computations and certified them. So this has Japanese quality. Okay. And now the question is, what about the rest? And I don't know. So I don't know, but thanks, because I did not plan to give this talk. I had a completely different subject on quasi-homomorphism, and one of the organizers asked me to talk about this stuff. And I was sitting over there preparing my talk. I looked at the back of the head of Andy, and this gave me an idea that, in fact, I know how to prove the next step here up to some factor. So what I can prove, it is working parts. But I mean, this is the idea, as I told you, it's not a very deep idea, so it's somehow stable. It's just a case-by-case shaking. Is that so what? Is that so? There exists an integer. There exists an integer. This one. This is 1, 2, 3. So let's call it 3. Such that if your starting genus is at least 5, you take any element here in this group LG1, then there exists an element phi in the next step. So it should MG1, 4. So just next step. Such that f to the n is, excuse me, this is g plus is g3, 1. So that f to the power n is equivalent to phi. Okay, so maybe you cannot show that every element is equivalent to one element a step down, but some fixed power is equivalent to someone down if you are willing to pay the price to go to a higher control genus, even if for the moment this G is extremely large.
What does that say? Sorry, after the MG 4.
The next step in the
The next
filtration.
step.
In case this is not 4 but 5, I remember.
And how big is n? You
How
say
fixed is?
this little n, so there exists some...
Oh yes, for the moment it's something like factorial 6.
Okay.
And somehow you will find these numbers. It has to do with the way you can understand the commutators of element in the Torelli group. down there when you project into the kernel of the map from the automorphism of nilpotent to the one step less. Okay, so this is work in progress. And since this is work in progress, there is hope in progress also to have the same at each step. And, namely that at each step, maybe if you are at one step, maybe you cannot prove easily that you are exactly in the next step, but some power, if you go increase utility heterogeneous, then it will fall. Because this is exactly the strategy I used and Morita used to prove these equalities. And what you get, in fact, in this case, is that any element here, you only have to increase the genus by 1. And the difficulty is that you need an integral. So the difficulty is, it's easy. It's long but easy to have this up to power 2. And the difficulty was to get rid of this power 2. Okay.
Is there a nice concept? I mean, your first theorem was like, wow, you get all homology spheres by a much more limited thing. Does this have something like you can build like a similar consequence?
No, for the moment, no. I don't know really. Well, yes, I have to but I think that a consequence is that, so if this is a proper filtration at some step, I think this would tell you that, and the hope in progress is true, is that this difference will never be detected by an invariant with rational values. So I would hope, my hope is to prove that there is a whole family of rational valued invariants of finite type, and my hope is at some point to prove that the rational invariants never vanish on these groups. So in this sense, so thank you for the observation. There is some clue about why is this filtration not a proper filtration. There is a theorem, but I never remember who proved it. Because so there isn't this theorem. So I don't remember the author, it's Otsuki or Murakami, I never remember which one. That says let lambda g into z be the function associated to the Casson invariant. Then, for any L, when you take the Torelli group, you have Casson invariant into Z, which is of course objective by construction. To go into your level L here, which is a proper subgroup, you restrict. And this is also subjective. So the Casson invariant never tells the difference between them, does not detect any step in these layers.
I mean, is this related somehow that there's the theorem of Hayne that says that you have the two filtrations of the Torelli group, one coming from the Johnson filtration, one coming from the lower central series.
Yes.
You define different topologies, and the Casson invariant is precisely detecting them.
Yes.
Okay.
Yes. And this theory of finite type invariants is somehow you could define them as invariants that vanish when you restrict to one of these lower central series of the Torelli group.
Right.
And the difference between Torelli and Johnson, we are exactly this.
So they derive this from Haynes results? Or?
So I don't derive, I read, no, it was really like, it's very elementary, but I never remember the proof. I have to find it.
Haynes results like all mixed Hodge theory, so it's not elementary.
No, this is really elementary.
Okay.
This is really elementary. Okay. Okay, so the state of art on this filtration is that the first three steps build everything. I guess the fourth step is somehow only a finite, at most a finite step, and there is absolutely no idea. Well, I guess it is almost finite, but I don't know. So I have to say that somehow my computations became very awful if you really want to have an equality. When Massuillot and Mellon published their work on classical calculus, I of course asked them if their methods could give you the next step, and he gave me this answer. Well, the computations are at the end as awful as yours, and we don't know if it works. Okay. Then let's go back and then let's build, let's construct the Casson invariant. So let's start with an arbitrary invariant like this. You associate this function fg, and they satisfy these obvious conditions. And the third condition now, because of the description of the equivalence relation that I, of course, erased, this splits into two. First, fg is constant under on the double classes, double cosets, T1 mod TA mod TD, and this is invariant under conjugation by an element in ABG1. Now the two constructions that control this equivalence relation of the Torelli. So let's now define this surgery instruction attached to fg, and define for any g larger than 3 fixed c index g of 5 psi. So on the Torelli group, this is 5 psi. 5 minus fg of psi, which is the surgery instruction attached to your invariant. Okay. So what are the properties of C of G, because it comes from an invariant? So you have the following on the maps CG. The first condition is this normalization issue. This is a normalized 2 cocycle, but I forget about this. First important condition is they are compatible, so CG plus 1 restricted to the Torelli group is CG. Second, because you have to be constant on double classes, so if this is in TAG1, then this has the same value as this, and this is 0 because you are building the 3 sphere, and therefore this has to be 0, and the same with psi on the other side. So CG is 0 on TAG1 times TG TG1. Then you have this condition on invariance. So because this is invariant under conjugation by ABG1, so is CG. Is invariant under conjugation by an element in ABG1. 4, well, the fact that this is a trivialized 2 cocycle. So you have a 2 cocycle, which whose cohomology class is trivial in H2 TG1n. And I will assume that n has no 2 torsion to avoid the problem with the Roy invariant. And the fifth condition is, well, it's true that CG is invariant under conjugation, and it is trivial. But it's not only CG that is invariant. One of its trivializations is also invariant. And the existence of an invariant trivialization, this is controlled by a one cohomology class, which is a torsor class. So the torsor in H1 of VG1 with homology in of VG1. N is 0. The set of all trivializations of your co-cycle is an affine space on this homomorphism group, and this is telling you that under the action of this group ABG there is a fixed point. Okay? Now, if there were two fixed points, then their difference would be a homomorphism invariant under the action of ABG1, but there is no such one. So if there is a trivialization which is ABG invariant, it is unique. And then the theorem says given a family of two cocycles on the Torelli group, such that all these are satisfied, then the unique ABG invariant trivializations glue back into an invariant. Okay? And if you accept to have two torsions, then you will have exactly two invariant trivializations because of the Rolling invariant. And these two families, they will also glue back, and you will have two invariants whose difference is the Rolling invariant. Okay. So how to use this theorem? Because when you prove it, you are very happy with this theorem, and then you realize that it is a little bit crazy, no? Because an invariant is a function on one variable satisfying a bunch of conditions. And I say, well, to construct this invariant, let's find a function on two variables satisfying a bunch of conditions that will give me this one variable function. But it turns out that there is a very natural candidate for such a cocycle. And this is the one. We have these results by Johnson. Did I tell about Casson and this strategy on the... No, oh, I forgot to say this. So I recently learned from one of the distinguished organizers that around Perelman, so around 0 Perelman, Casson was working on a strategy to prove the Poincare conjecture precisely using the Johnson filtration. And he gave a talk on this, and of course never published the results. So if someone has a hold on these notes, I would be very interested. And not only I would be very interested in knowing what was his strategy. I think one way to attack this Poincare conjecture would be to say that if you build a homotopy sphere, then you can go arbitrarily low in this Johnson filtration, but without the genus tending to infinity. So you would need to bound this GK. And in my hope in progress, this GK tend to infinity and rather quickly. Okay. So Johnson tells us that the Abelanization of the Torelli group is the third exterior power of n. Plus before in the Abelanization, but I get rid of these two torsions. So I have my surface embedded in S3, and of course attached to it I have two Lagrangians. The one attached to this curve AI, and one attached to these curves BG. So N1, I write it A plus B. And therefore this lambda 3 of n, I write it as a direct sum, lambda 3 of A, direct sum, some mixed term with A and B, plus lambda 3 of B. And I will give you a two cocycle of this group. So a two cocycle, the easiest way is to give you a bilinear function. So this is it, the matrix, 0 everywhere. And here you have a pairing between B and A induced by the intersection form. So this is lambda 3 of omega. Omega is into Z. And I call this Gj. And you can see very easily that this is the unique Tuco cycle on the abelianization of the Torelli group that, when pulled back to the Torelli group, satisfies the first three conditions. The fact that you are zero on these groups is that when you look at the image of these groups TA, G1 and TB, G1, TA lands here and TB lands here. So if on the left you have something in TA, so it contributes to 0 here, and if on the right you have someone in TB, then this is 0, and this condition is obviously fulfilled. And then a consequence now of Haynes construction, of Haynes computation, rational computations, is that if you pull back 2 times G of G, this is 0. Basically because it lives in a sufficiently low genus where the map from the second cohomology of N1 into the Torelli group is rationally trivial. And because this cocycle is stable, then it has to be always trivial. And then you have to work a little bit harder to see that it is 2. And then harder is the torsor is trivial. But it's not very hard. And then the unique trivialization glues back into an invariant because of the theorem. But this theorem is characterized by the surgery property, and then you check that it's exactly the same surgery condition that the one given by Casson for his invariant. So you constructed the Casson invariant. And the fact that you have a 2 here, this is again a trace of the Rowley invariant. Because if you reduce the Casson invariant mode 2, then you have a guy that is a homomorphism. So the reduction mode 2 of the surgery instruction has to be 0, and this explains this too. Okay. Thank you very much for your attention.
Are there any questions?
So which of Haynes' computations is this?
Well, in this paper on hot structures and the rational Lie algebra,
Yeah.
well, he shows that when you have the map from H2 of N1 in for G equals 3 into H2 of the Torelli group Q, this is 0.
Ah, yeah, I get it.
And this is exactly what you need.
Okay.
Because this cocycle lives here, so its image is 0, but then it is stable, so it will be always be 0.
Okay.
So I wonder how did this filtration interact with trying to study the integral homology spheres up to homology cobordism, where they spent a lot of work in
I don't know.
three-dimensional topology, right?
Yes,
Hugely complicated cobordism group.
I really don't know. I really don't know.
Seems to be a different world.
Yeah.
Yes.
I mean, Marita does have some conjectures about this, so which I do not remember off the top of my head.
On the interaction between the
Yeah.
Johnson-
He had ways of using the Johnson filtration to get invariants of homology, cobordism invariants, but I'm not sure if they've ever been worked out. I've seen them in lectures.
Yeah, I just would like to make a comment because if I remember correctly, and I think I do, is that the Casson is a homomorphism on KG1.
Oh yes. But this is a consequence of the construction I gave before.
Yeah, I just want you to mention this.
Yes,
Yeah.
of course, yes, because you see this, when I construct the Casson invariant by trivializing basically this cocycle, okay? Well, if you go to KG1, it is in the kernel of the abelianization map. and therefore the surgery instruction vanishes on this subgroup, so it becomes a homomorphism. Yes, in KB1, LB1, wherever.
I think since people might not know the history, should we point out that that theorem is due to, well, Morita, but also an unpublished work of Paul Kirk and Dance Johnson, so.
Okay.
It's a non-trivial theorem, so.
Yeah.
Any other questions? Okay, let's thank the speaker again.